Okay, so look around your neighborhood. Seriously, next time you're out, maybe walking the dog or driving to the store, just count the rooftops. You'll see them everywhere, those dark blue rectangles. Solar panels are, I mean, uh, they've basically become the suburban standard, haven't they?
Oh, for sure.
It sort of feels like the technology has finally arrived.
Yeah.
You know, like we've crossed the finish line, and this is just what the future looks like.
It definitely feels that way. It's so visible, so tangible. But, if you actually dig into the research stack we pulled for today, the engineering reports, the market analysis, you realize pretty quickly that what we're seeing right now, that is just stage one. We are, and I mean this, we are standing at the very beginning of a massive shift in what solar energy actually is.
And that's really what we want to get into with this deep dive. We're looking at this whole stack of sources on emerging solar tech, and the headline isn't really about more panels. It's about a fundamental change in intelligence.
Exactly. The best analogy I saw in the sources, the one that really clicked for me, was the difference between a pocket calculator and a smartphone.
Okay, I like that. Let's unpack that.
Yeah.
Because to the untrained eye, a solar panel is just a slab of silicon. It sits there, it gets hot, it makes electricity. It's a commodity.
Right. And that's the calculator phase. It does one job, it's useful, but it's dumb hardware.
Yeah.
It doesn't talk to the grid, it doesn't analyze weather patterns, and it definitely doesn't predict the future. The smartphone phase is where we are heading now. We're talking about a convergence where solar becomes this connected, intelligent ecosystem.
So we're moving from just making electricity to intelligently managing it. And looking at our outline, the drivers here seem to be AI, advanced storage, and some, frankly, pretty wild new hardware.
That's the triad. And it's necessary because, let's be honest, the sun has some stubborn problems that simple glass rectangles can't fix on their own.
Let's start right there then. The problem with the sun. It sounds like a bad sci-fi movie title, but for a grid operator, it's a daily operational nightmare. What's the core issue?
Well, it really just boils down to two huge headaches for the utilities: variability and dispatchability.
Okay, hold on. Dispatchability. That's a classic industry term. Break that down for us in plain English.
Sure. Dispatchability is simply the ability to turn a power source on or off when you want. If you're running a gas plant and everyone turns on their air conditioning at 5 p.m., you open the valve. You dispatch more power to meet that demand.
But you can't turn up the sun.
You can't turn up the sun.
Yeah.
Precisely. You get what you get. And historically, that has been the hard limit for solar. It's non-dispatchable. You can't control it, so the grid has to treat it like this chaotic variable. It just creates uncertainty.
And this is where I assume artificial intelligence enters the conversation.
Right. AI is becoming the, you could call it the brain of the solar farm, and the first place it really changes the game is in forecasting.
But wait a minute. We've had weather reports for a century. I can check my phone right now and see if it's going to be cloudy this afternoon. How is AI forecasting really any different?
It's a difference of resolution and data density. Traditional forecasting is macro. It looks at big pressure systems over a whole city. AI forecasting for solar is hyperlocal. It's ingesting satellite imagery, tracking individual cloud vectors, monitoring wind speeds that cool the panels. It's even looking at the historical output of that specific solar site to predict what it's going to do.
Whoa. So it's not just saying partly cloudy, it's saying that specific cloud will shade panel array Y at 2:04 p.m., causing a 12% drop in voltage.
Exactly that. It's predicting the output minute by minute.
And why does that level of precision matter so much? Is the grid really that sensitive?
It is, because uncertainty is incredibly expensive. If a grid operator doesn't know if solar production is about to fall off a cliff, they have to keep a fossil fuel plant running in the background, just idling, just in case.
Ah, the spinning reserve.
That's the one.
It's like keeping a taxi waiting outside your house all day, just in case your car doesn't start.
That is a perfect analogy. And you're paying that taxi meter every single minute it sits there. AI forecasting gives the operator confidence. They know exactly what the solar will do, so they can tell that taxi to go home. It lowers costs and emissions without installing a single new panel.
So that's the prediction side. But the notes also mention optimization. This implies the AI is actually, touching the controls, not just watching.
Oh, it is. It moves from passive observation to active decision-making. On a large utility-scale farm, you have trackers, these motors that tilt the panels to face the sun.
Like a sunflower, which seems pretty optimal.
Usually, yes. But the AI realizes that sometimes looking directly at the sun isn't the best move. Maybe it's an overcast day with diffuse light scattering everywhere.
Right.
The AI might flatten the panels to catch all that scattered light, generating more power than if they were pointed at where the sun's hiding. Or it might adjust to avoid casting a shadow on the row behind it. Little things.
So it's making these real-time tactical decisions to squeeze out every last drop of efficiency.
And it does this on the demand side too. This is where it connects to the whole smart home idea. The AI sees a spike in solar production coming at noon. It decides, okay, let's run the HVAC a little harder right now to pre-cool the building. Or it tells the EV charger to ramp up. It matches consumption to generation automatically.
That's clever. It solves the dispatchability problem by moving the demand to meet the supply instead of the other way around.
Exactly. And it protects the investment too. We have to talk about predictive maintenance.
I was interested in this.
That's
Because
it.
normally you fix a solar panel when you see the output drop to 0, you wait for it to break.
Which is reactive maintenance. It's slow, you have to roll a truck, and you lose revenue while the panel is down.
Right.
AI flips this. It monitors the electrical heartbeat of the system voltage curves, current temperature patterns. It can spot the signature of a fraying table or a corroding connector weeks before it actually fails.
So you fix it during a scheduled visit, not an emergency outage.
It converts an emergency into a to-do list item.
Okay, so we have the brain. The AI predicts, optimizes, protects. But even the smartest brain can't make the sun shine at midnight. We still need to store all those electrons.
Which brings us to the muscle. Energy storage. This is what finally makes solar a 247 resource.
Now, when I hear storage, my mind immediately goes to lithium-ion, the same stuff in our laptops and cars. That seems to be the standard.
And for homes and EVs, yeah, lithium-ion is the undisputed king. It's energy dense, it reacts instantly. But the source material is pretty clear, that lithium isn't the silver bullet for everything. It has issues with degradation, it just wears out, and it gets really expensive to scale up for massive grid storage.
So if we want to power a whole city through the night, what's the alternative?
For the really heavy lifting, the research points to flow batteries.
Flow, so that implies liquid. How does that work?
That's the key difference. In a lithium battery, all the energy is stored in the solid electrodes. In a flow battery, the energy is stored in liquid electrolytes held in these big external tanks. The liquids then flow through a central stack to generate power.
And why does that matter? What's the advantage?
It lets you decouple power and energy. If you want more storage capacity, say, to last for 12 hours instead of 4, you don't buy a whole new battery, you just build a bigger plastic tank for the liquid.
Huh. That sounds much, much easier to scale.
It is. They're fantastic for long-duration storage. And they don't degrade like lithium, so they can cycle every single day for decades.
And then there are the more low-tech solutions. The notes mention pumped hydro and thermal storage.
Yeah, never underestimate gravity. Pumped hydro is the oldest and biggest battery we have. You use excess solar during the day to pump water up a hill into a reservoir. When you need power at night, you just let it flow back down through a turbine.
Water battery.
A giant water battery. And thermal storage is similar, using extra energy to freeze massive blocks of ice or heat up molten salts, which can then be used to cool or heat buildings later on. It's super efficient because you aren't converting energy forms back and forth. You're just moving heat around.
So we have the brain, the AI, and we have the muscle, the storage. But how does this all actually plug into the wall? The sources talk a lot about smart inverters being the nervous system.
This is such a critically overlooked piece of hardware. The inverter's job used to be so boring. Just take the direct current, the DC from the panel, and flip it to alternating current, AC, for the house.
Simple translator.
Exactly. But the new generation of smart inverters are two-way communicators. They are constantly talking to the utility grid.
And why does the utility need to talk to my inverter? That sounds a little intrusive.
It's all about keeping the grid from crashing. As we add more and more solar, we get voltage spikes, the grid gets noisy.
Okay.
A smart inverter provides what engineers call grid support. It can inject reactive power to smooth out those voltage bumps. It can ride through minor disturbances instead of panicking and just shutting off.
So instead of the solar system being this burden that the grid has to manage, the inverter is actually acting as a shock absorber.
Precisely. It allows us to put way more solar on the grid without destabilizing it. And when you network enough of these smart inverters and batteries together, well, that's when you get to the most disruptive concept in this entire stack.
I think I know where you're going. Virtual power plants, VPPs.
This is the genuine aha moment for the entire industry.
All right, walk us through this. How can a power plant possibly be virtual?
Okay, think about how the grid works today. Hot summer day, everyone turns on the AC, demand spikes, the utility has to turn on a peaker plant.
Right. Usually some big, dirty gas plant that sits idle 90% of the time, just waiting for that one hot afternoon.
Exactly, and we all pay for that idle time through higher rates. A VPP flips the script. Instead of building one giant plant, a VPP uses software to aggregate thousands of small existing devices. Rooftop solar, home batteries, smart thermostats, EVs plugged into garages.
So it takes 10,000 tiny batteries and makes them act like one big one.
You got it. The utility sends a digital signal. We need 50 megawatts now. And instantly, thousands of batteries in people's basements discharge a few kilowatts each, or thousands of thermostats turn down by 1 degree. To the grid operator, the result is identical to firing up that gas plant.
That is mind-blowing. It's decentralized physically, but it's coordinated digitally.
And it pays the participants. If you let your battery be part of a VPP, you get a check or a bill credit. You are literally renting out your storage to the grid.
It transforms the homeowner from just a passive consumer into an active supplier.
And it adds resilience, which links directly to the idea of microgrids.
The power islands.
Exactly. A microgrid, say a university campus or a hospital, can operate while it's connected to the main grid, but if a storm knocks the main lines down, it can just disconnect. It islands itself. Using its own solar in storage, managed by that AI brain, it keeps its own lights on while the rest of the city goes dark.
That's not just about saving money anymore. That's a massive safety feature.
It changes the grid from like a fragile glass vase into a chainmail mesh. It's much harder to break.
I want to pivot a little here. We've talked software, storage, and grid architecture, but I have to ask, what about the panels themselves? I mean, we're still using silicon technology that was invented in the 1950s. Are we just stuck with the blue rectangles forever?
Not for long. We're getting really close to the theoretical limit of silicon efficiency. It can only convert so much sunlight into power. About 29% is the hard ceiling. To break through that, we need new materials. The buzzword you need to know from the research is perovskites.
Perovskite sounds like a mineral from a geology class.
It is a crystal structure, yeah. Perovskite materials are potential game changers because they're cheap to manufacture. You can essentially print them like ink instead of baking them like silicon. They're lightweight and they can be flexible.
Flexible solar. So you could, wrap a column in it?
Potentially. But the immediate application that has scientists really excited is tandem cells. Think of it like a razor with 2 blades. You stack a thin layer of perovskite on top of a layer of silicon.
Why stack them?
Because they're tuned to different parts of the light spectrum. The perovskite layer captures the high-energy blue light, and then it lets the red spectrum pass straight through to the silicon layer underneath.
So they aren't competing with each other, they're collaborating.
Exactly. By working together, they can capture more energy from the same square foot of sunlight than either could on its own. We're already seeing lab results smashing through that 30% efficiency barrier.
That is a huge leap. And does this change where we can put solar if the panels are lighter and more efficient?
Completely. And we get into this world of BIPV, building integrated photovoltaics.
Right. This is where the building materials themselves are the solar panels.
Yes. Solar roof shingles that look just like slate. Solar glass for windows. Facades that generate power. It stops being an ugly rack bolted onto your roof and it becomes the architecture itself.
I also saw something in the notes about floating solar and agrivoltaics. Are these just niche ideas or real solutions?
They're solving the land use problem. Floating solar putting panels on reservoirs is brilliant. The water cools the panels, which makes them more efficient, and the panels shade the water, which reduces evaporation.
A win-win, especially for drought-prone areas like California.
And agrivoltaics is putting panels over crops. You mount them high enough for tractors to pass underneath. They provide partial shade, which certain crops like berries or leafy greens actually prefer. It reduces water usage for the farmer, and they get 2 harvests, food and energy.
It seems like we're just getting so much smarter about how solar integrates into the world rather than just paving over fields with glass.
It's all about dual use. Land is a finite resource. You have to share it.
So let's bring this down to the listener. We've covered a lot of tech, AI, flow batteries, perovskites. What does this actually mean for the person listening to this deep dive right now? Why should they care if their neighbor has a smart inverter?
Well, for the homeowner, it really points toward this automated, energy-savvy living. It's the set it and forget it lifestyle. You won't have to watch the meter anymore. Your AI will buy power when it's cheap and sell it when it's expensive. Your car will just charge itself at the optimal moment.
It turns energy arbitrage into just a background app on your life.
And for businesses, it's all about the bottom line, reducing those demand charges and making sure you don't lose a ton of money when the grid goes down.
There's also a business model shift mentioned here, energy as a service.
This one is huge because it addresses the biggest hurdle, cost. Not everyone has 20 grand to put solar on their roof.
Right.
With energy as a service, a company installs the battery and solar on your house for free. They own the hardware, you just agree to pay a flat rate for your power or buy the energy it generates.
So it treats solar like a subscription service, not a huge home renovation.
Which is absolutely crucial for equity. We have to make sure the renewable transition isn't just for the wealthy. And things like community solar allow renters or people with shaded roofs to subscribe to a shared solar farm nearby.
And those VPP programs we mentioned, that's a way for people to actually earn revenue from the grid, which helps offset the costs.
Exactly. The AI tracking ensures those benefits can be distributed fairly. It creates real transparency in the market.
So let's zoom out and just summarize this journey. We started with the observation that solar is everywhere. But the real takeaway here seems to be that the physical panels are just the tip of the iceberg.
That's the summary. We are moving from stage 1, passive hardware, the calculator, to what you could call stage 3, the intelligent ecosystem, the smartphone.
The value is shifting. It's no longer just about generating a kilowatt hour. It's about the flexibility of that kilowatt hour.
Right. Can you store it? Can you dispatch it? Can you predict it? That is where the value lies now.
It fundamentally changes the question for the consumer. It used to be, should I get solar panels?
And now the question is, how can I integrate my home into the energy network? We are moving toward a future where the grid isn't just a utility that sends you a bill. It's a marketplace. And thanks to this tech, we're all about to become participants.
We're not just plugged in anymore, we're part of the circuit. And that is a fascinating place to be. Thanks for guiding us through the stack today.
Always a pleasure.